Hi all, I want to give a short example of a more involved extreme value theorem example. This will involve optimizing a function on an unbounded set. It still remains closed, but where we first have to actually prove that the maximum exists, and then we have to use the proof of extreme value theorem, not its statement, to prove that we actually get a maximum. But this often requires more careful estimates and more careful analysis. It's more involved, but it gives a better sense of what is actually happening. So for the final example, I had to correct this a little bit, but for the final example, if we are looking at, let's consider a maximization problem on all of R2 of the following function, x1 divided by 1 plus x1 squared plus x2 squared. Now, R2 is closed, well, it's the whole space, but it is not bounded. So there's no need for this to be maximization problem to have actually a solution. But let's analyze what is this more carefully. So it does not need to have, but in this case, actually it does have. So first step would be to look at that this function is bounded. It is continuous. It's a ratio of continuous functions, and so that can be proven. But to do that, it makes sense to divide the space into regimes where you can get some estimates. And this is controlled by the fact that you look at the expression and you want to estimate the denominator from above or the numerator from below. So one case that makes sense is that we look at when x1 is actually very big or bigger than 1. If x1 is bigger than or equal to 1, then we get that the function is x1 bounded from absolute value of x1 divided by its numerator. Now, because x is bigger than or equal to 1, we can estimate the absolute value by the square from above. And we can estimate the numerator by 1 plus x1 squared. The numerator is now bigger than the denominator, so this whole thing is less than or equal to 1. Great. So we get an upper bound of 1. I mean, this is not the best upper bound, but it is some upper bound that we get from this. So this leaves us with this strip of values. But next we might want to look at the case when x1 is bounded by 1, but x2 is bounded from above, bounded from below by 1. And in that case, while the numerator is bounded from above by 1, because x1 is bounded from above by 1, and the denominator is always bounded from below by 1. So we get that 1 over 1 divided by 1. So on the blue set, we get that bound. And what we're left with is the green set. Now on the red and the blue, we are bounded, but the green set is compact. So what we can get is that the suprema of the function is the maximum of the suprema on the red set, the blue set, and the green set. And why this is the case is that every point in R2 is either an element of C, or in B, or in A. In other words, this is equal to the union of those. Now, we gave upper bounds for the values in these parts. So in C, we got an upper bound of 1. In B, we got an upper bound of 1. And in A, well, it is a closed and bounded subset, so it has some upper bound. So this function now is bounded. So being bounded, that's kind of the first step of having a maximum. Now let's prove a maximum exists. Well, because it is bounded, there still exists a Pn, a sequence Pn, so that limit as n goes to infinity of Pn, Fpn is equal to the suprema. Because this is found, now this is a bounded thing, so that we can find such a sequence. If it was unbounded, you could find a sequence of points where the function will go off to infinity, and this is sometimes another useful way of looking at this. Now what we want to do is we want to find something, a convergent subsequence of this. Well, To do that, we have to show, we want to show that Pn is actually bounded. So we cannot use the fact that closed and boundedness now because this is just a sequence of points in R2. So we have to now use this particular function. And this indicates the difficulty in general, if you want to prove that maxima are attained, is that we want to make sure that the points cannot go off to infinity. And to do this, there's a common scheme. Let's plug in one particular value. So f of, say, 1, 0 is equal to 1 over 1 plus 1, so it's 1/2. And we will use this now in the following way, that if we modify our definitions of A, B, and C, so A is now the points x, y, where absolute value of x is less than 2, and absolute value of y is less than 2. Let's make it actually 3 to really drive this point home. B is the set x, y, where one of these fails, so absolute value of x is bigger than 3. And C is what remains, so absolute value of x is less than or equal to 3, but absolute value of y is bigger than or equal to 3. Okay, again, R2 is the union of A and B and C, because every point satisfies one of these combinations of inequalities. But if P belongs into B, then f of P will be less than or equal to absolute value of x and 1 plus absolute value of x squared, which will be less than 1/3 absolute value of x squared, because now absolute value of x will be squared is less than 3 absolute value of x. Yeah. Sorry, the wrong way. So absolute value of x is bigger than or equal to 3. We'll multiply both sides by 3 by absolute value of x. So we get absolute value of x squared is bigger than or equal to 3 absolute value of x, and divide by 3. That gives us a bound for the numerator. The denominator we just bound by x squared. So we get 1/3. So supremum. So in B, all the function values are less than 1/3. Similarly, if P is in C, then f of P is at most 3 divided by 1 plus 9, which is less than 1/3. So what we get is that in these two sets, B and C, the function is less than 1/3. But the maximum of fp has to be bigger than or equal to f of 0, 1, or the supremum here. One should write a supremum here, which was equal to 1/2. So if Pn are so that limit n goes to infinity, f of Pn is equal to maximum or supremum, then there exists an n such that f of Pn will be bigger than or equal to 1 over, well, not necessarily bigger than 1/2, but strictly bigger than 1/3, because the maximum is 1/2 and 1/3 is strictly less than that. But because f of Pn is bigger than 1/3, this means that Pn is actually after this index in A. And A is closed and bounded, so it is compact, and there exists a convergent subsequence. So this concludes this more involved example.